Hi guys. So I'm not in the classroom, but I didn't want to leave you hanging because I guess Mr. Childress is not back yet, and not knowing who was going to be in the room with you, I wanted to be sure that you had a way to keep progress with your content so you don't get too far behind. So at least for the next few days, I'm going to be narrating some things on video like this, and then directing you so that you can do the same sort of stuff that you've been doing all the semester, all the term so far, and practice on some worksheets. So everything you need is still getting uploaded in Google Classroom. I'm here going to tell you about a subject called geometric sequences. It sounds scary, but it's not. So hang with me for a second here. I'm using the PowerPoint slides that are in Google Classroom because they have good stuff in them. I'm going to walk you through the information you need and then let you have at practice problems. And whoever's in the room with you, if they're not really a math person, they should follow along and be in a position to possibly help you out too. So I'm just going to get going here. I also want to sort of mimic for you the process of writing down notes, because I'm just going to be babbling based on what's on the screen. You should write stuff down as you go along, as I go along, so that you have something to work with when you have to apply these ideas for yourself. So every little while, I'm going to interrupt myself and say, if I was taking notes, here's what I would be writing down right now, so that you can hopefully mimic it. So you'll want a blank piece of paper or 2 or 3 nearby. So here we go. So I warned you that geometric sequences sound scary, but they are not. A sequence is just a list of numbers. You can make up your own. 18, 47, -12, square root of 9. Well, that's 3, so that's dull. Square root of 10, that's better. It's just a list of numbers. That's what a sequence is. A geometric sequence is a list of numbers that has a very noticeable pattern to it. And that pattern is what we're going to look for. Okay, so this is very wordy, but a geometric sequence is a list of numbers in which each number in the list is just the previous number multiplied by some other number. And that number that's being applied term by term by term in this list is the same as we go along. Okay, so there's 2 things that we're going to be counting. One is just how far along are we in the list. So are we at number 1? Are we at number 2 in the list? Are we at number 3 in the list? Are we at number 4 in the list, right? That's one thing we're going to count. And then the other thing we're going to observe is, what is that first or second or third number in the list? Okay, so looking at the middle of this slide here, say our first number is 3, our second number is 6, our third number is 12, our fourth number is 24. Can you already look at the 3, 6, 12, 24 and see that that is a list of numbers where every number is just the previous number multiplied by some value? Okay, and figure that out. Well, let's just look at the first 2. To get from 3 to 6, what do? You multiply by 2. Let's see how that works from there on. If we take 6 and multiply it by 2, we get 12. Aha, that's the next number in the list. And we take 12 and multiply it by 2, and we get 24. Aha, that's the next number in the list. This is a geometric sequence. It's a list of numbers with a very distinct pattern to it, and that pattern is the number that you're multiplying by each term to get to the next number in line. Now, the thing at the bottom here is a little cryptic until you see what's happening. This is just the tidy descriptor of what's going on. So the red n, the subscripts, n and n minus 1, those are the counters of the number that we're on. Are we at the first number? Are we at the second number? Are we at the third number? So a with a little 5 as the subscript is the 5th number in the list. The value r that's in that recipe is the number that we're multiplying every number by to produce the next number in the list. So for this set of numbers here, and in the middle, the 3, 6, 12, 24, 24 is A4. A is just the generic letter that's going to represent our numbers. and it's the fourth one in the list, 3, 6, 12, 24. And the number 2, that's the multiple that we use to leapfrog from number to number to number, that R is 2 because we're multiplying by 2. So if I was taking notes, what I might do here is write down that list. 3, I'll show you in a second here. Got to get it started in my brain. 3, 6, 12, 24. Okay, so, look at these two numbers. 6 is 3 times 2. And then 12 is 6 times 2. And then 24 is 12 times 2. So what's happening is that we are getting every number in the list by multiplying the previous number by 2. And that tells us that R, the ratio, is equal to 2 in this geometric series. If we want to start labeling these in terms of just counting the list itself, remember, A is the generic placeholder for one of these numbers in the list. So the 3 is A1. The 6 is A2. The 12 is A3. The 24 is A4. And now with this lettering, we can continue the list, right? A5 would be A4 times R, the previous number in the list, times R. And the previous number is 24. We're going to multiply by that magic 2. So the next number in this list that isn't shown yet would be 48. And then A6 would be, can you get me there without the intermediate stuff? 48 times 2, 96. Okay, and then this list would continue. These never have to end. In a few minutes, we'll see, okay, this is fine to list them out one at a time, but what if we just wanted to leap out to entry 100 in the list and learn what that is? Is there a way to do that? And the answer is yes. Okay, but this is a geometric sequence. It's all about pattern recognition. List of numbers, discover the number that you're multiplying with to get from term to term to term in the list. So, for example, 1, 3, 9, 27. We're going to discover R. If you just look at 1, 3, 9, 27, you already might know what's the number that we're multiplying with to get from number to number. But if it's not clear, just grab a couple of numbers, divide the next one in line by the previous one, and see what that multiple was. So if I have, again, I'm taking notes here. If I have the list 1, 3, 9, 27, and so on, and I'm trying to ask what the heck is R, and maybe I don't see it yet. Okay, should be kind of clear already here, but I'm just going to pick the 9 and the 3. Here, grab those two, and say, well, 9 divided by 3 is 3. Okay, fine. So maybe the ratio is 3. Let's check that out. Now let's grab the 9 and the 27. The 27 divided by the previous number is 9. Well, hey, that's 3 too. And so what we're seeing is that every number in the list is being multiplied by 3 to get to the next one. So R is 3. We've got A1, A2, A3, A4. A5 would be 27 times 3. 81? Something like that. The second list here is a little bit trickier because now the ratio is less than 1, and oh my gosh, there are negative numbers built in. Okay, so I'm starting to make my notes of this example. Whoops, wrong page. There we are. So 16, -4, -1, +1/4, and so on. Do you see the pattern already? Every number in this list is the previous number times some ratio. That ratio could be bigger than 1 or less than 1. Could be positive, could be negative. So this example is kind of bundling everything up. But let's just, we're after what the heck is R. Okay, so let's just compare some numbers that are right next to each other. For example, if I grab this -16 and the 4, the idea here is that we would take the -16, we would multiply it by this mystery ratio, and we would get 4. What number can we multiply by negative 16 to produce a 4? Well, certainly there has to be a 1/4 in there, because 16 times 1/4 is the 4, but there's also the fact that the 16 was negative, but the next number is positive. So that means that this ratio is probably negative 1/4, because that flips on and off the minus sign as we go down the list, and it also scales each number by 1/4. So the first pair of numbers suggests to me that the ratio from term to term is negative 1/4. So, double check these two. To get from 4 to negative 1, would we take 4 and multiply by negative 1/4? Yes. To get from negative 1 to positive 1/4, would we take negative 1 and multiply it by negative 1/4? Yes. Okay, so that value of negative 1/4 is the correct one. And just to give a flashback here, remember this recipe at the bottom is telling the whole story, that the next number in a sequence is the previous number times this value called the ratio. That ratio can be bigger than 1, less than 1, positive, or negative. Okay, a couple more examples. Let's extend the series. Here's a series that leads with 5, negative 10, 20, negative 40. We're going to find the ratio and then construct the next two terms. So 5, negative 10, 20, negative 40. I'm writing this down. I'm taking my notes. So there's my list so far. We want to know what are the next two numbers in this list. So we need to know R first of all. R is the number that when we start with 5, what do we multiply by to make number 10, to negative 10? Does that same number multiply negative 10 to give us positive 20, and then multiply 20 to give negative 40? Can you figure that number out? I'm just going to say it. It's negative 2. So the 2 part of it explains the 5 to 10 to 20 to 40. We're doubling our numbers every time in size, but we're also turning on and off that negative sign. And so 5 times negative 2 gives us negative 10. Dogs are barking. They do this every time I get on the microphone. Negative 10 times negative 2 is positive 20. Positive 20 times negative 2 is negative 40, and so on. So what are the next two numbers? Well, the first mystery number is going to be the negative 40 times the ratio. Negative 40 times negative 2 is positive 80. And then the next number after that is this number times negative 2, so that next number is negative 160. Now he's come in to say hi. The next example here looks a little bit more gruesome. The point of it is to make sure you're not shy about getting computational help when you need it, say with a calculator. Okay, so what is the ratio of this sequence, and can we find the next two mystery numbers in the sequence? All right, so we need to discover the mystery number that makes this happen. If we start with the first in the list, 512, and multiply by R, our mystery number, we need to get the next number in the list, which is 384. Whoops, I'm not showing you this. There we go, down here at the bottom. 512, 384, 288. So 512 times what mystery number gives us 384, and then also that 384 times the same mystery number is supposed to get us 288. What is this mystery number? Okay, well, take either one of these, take your pick, and figure out what R is. I will start with this first one. This tells me that R is 384 over 512. Now, that looks kind of gross, but you have a calculator nearby, probably. I have one on my screen. I'm not going to show that screen. I'm already getting confused about flipping back and forth. But if I do 384 divided by 512, I get 0.75, or 3/4. Okay. Does that same number work for this? Well, now I'm going to do 288 over 384. That also is 0.75. So 0.75 works. That is the ratio. So if we want the next two numbers in the list, we just keep the ball rolling. 288 times the ratio 0.75 is the next number in the list. So 288 times 0.75 is 216. And then 216 times 0.75 is 162. So we've recognized what the ratio is, and we've extended the sequence by two more terms. That's the game. By the way, since this video has a link in Google Classroom, you can always go back and take a look at some of this stuff again if you need to. Okay, so the original issue was that we've tackled now is here's a list of numbers. What's the pattern? What is the ratio that we multiply a previous number by to get the next number? And then you just leapfrog down the line, making more and more numbers in your sequence. If you have a sequence and you're curious about maybe what's the 25th term in this list, I don't want to see the 19th and the 20th and the 21st. I just want to go figure out the 25th term. Recognize what's happening with this process is that I'm going to switch pages on my notes here and then show you. This isn't really taking notes for you. This is just me doing a quick demonstration. But let's say I had a first number in my list is 2 and a ratio is 1/4. Okay, then A2 is going to be A1 times R, which is 2 times 1/4. I'm not going to simplify this. A3 then becomes A2 times R. Now, A2 was that number. So this is 2 times 1/4 times 1/4. And that is 2 times 1/4 squared. If we use this number to produce A4, what we're going to do is multiply by 1/4 again. So the progress through this list is simply stacking up powers of your ratio. And so that's why this formula looks slightly different. The previous formula says if you know, say, A6, you can generate A7. If you know A9, you can generate A10. This one says, look, if you know the ratio, you can start with the first number in your sequence and leapfrog yourself all the way to any other term that you want simply by stacking up all those powers of the ratio all at once. And notice this says, for example, what is available on this pattern, like right here. Let me switch colors just to make sure we can see it, right? When we calculated A3, we ended up with our ratio being squared. A4 would need one more power of that ratio 1/4, so A4 would come from a 1/4 cubed. So the counter for where you are in the list and the exponent on the ratio that you need to get there, they're one off of each other, right? So that's why this formula looks the way it does. This says, look, if you know the first number in your sequence and you know the ratio, you can leap anywhere. If I want the 10th entry in the sequence, I write down the first entry and then multiply it by my ratio to the 9th, right? If I'm looking for the 10th in the sequence, I multiply by R to the 9th. If I'm looking at for the 30th number in this sequence, I'm going to multiply with the ratio to the 29th. Okay, they're off by 1. So what can we do with this? Well, here we go. The first term of a geometric sequence is 128, and the common ratio is 0.5. What's the 10th term in the sequence? So here comes my note-taking for this example again. I'm going to write down this formula, A sub n equals A1 times R to the n minus 1. Sorry, it's still in red. That's kind of obnoxious, but I'm not going to fiddle with it. And for our example, we have a sequence where A1 is 128 and R is 0.5. And we want to know the 10th term in the sequence. So what is A10? Well, according to this formula, A10 is going to be A1, which was the original 128, times our ratio, which is 0.5. And then remember this business, if we want the 10th term, we're going to use the ratio to raise to the 9th. So there we go, 128 times 0.5 to the 9th. What does that number look like? Well, again, that's a calculator job. Let me tell you what it is, or you can try it out to make sure you get the same thing. 128 times 0.5 to the 9th, I get 0.25, which is 1/4. So what this means is this sequence starts at 128. Every number in the list is half of the previous number. So 128 to 64 to 32 to 16, etc., etc., etc. By the time we've done that out to the 10th number in the list, we're already down to 1/4. And to figure that out, we did not need to know every single number in between. So that's pretty cool. I'll show you an example of the ever-present question, well, why? Why do we want to know how to do this? Okay, I'll give you an example in a couple of seconds here. Two more examples. What's the 13th term of this sequence? 8, -16, 32, -64. So this is sort of the broad question that we're going to wrap up with. That was to listen for the applause. All right, so we're looking for the 13th term in the sequence. And so this is that, version 2 of the geometric sequence formula is if you want to just leapfrog all the way out. You need to know the first term and you need to know the ratio. So you can raise that ratio to the right exponent. So again, I'm taking notes here. You'll see them in a second. I want to make sure I get them jotted down. So I don't have to flip back and forth. Okay, so here are my notes about this problem. I'm given the sequence that starts with 8, -16, 32, -64. What is the 13th number in this sequence? Now, I could just sit here and calculate the 5th and the 6th and the 7th and do that all the way out to the 13th. Or I want to leapfrog right to the 13th. In order to do either of those, I need to know the ratio. What is this mystery multiple that gets us from one number in the list to the next? Hopefully by now, if you look at these numbers, you can see that that ratio is -2. 8 times -2 gets us to -16. Then we multiply -16 by -2 to get us to +32. So r is equal to -2, and we'll call that good. And again, remember, if you're puzzled by that, just pick any two neighboring numbers, divide the next one in line by the previous one in line, such as divide 32 by -16. That will show you the ratio that's being used to climb from number to number. Okay, so according to the leapfrog formula, if we want to get out to A13, we need to start with A1, and the process of getting out to 13 would be multiplying by this ratio 12 times. Okay, remember that offset. Remember right here at the top of this screen. By a strict reading of all the letters in here, if we want A13, where n is 13, we're going to apply the ratio 12 times. Okay, so what is A1? Well, this is the first number in the list. 8 times -2 to the 12th. Again, calculator time. You can't see what I'm doing, but I'm typing in the -2. I'm doing -2 to the 12th first, just to make sure I get it right, and multiplying that by 8. And that value is, oh my gosh, 32,768. That's the 13th number in the list. Okay, why? Why would you want to do this type of process? Well, here's an example in the PowerPoint slides. You can read it. I'm going to actually tell you about a different example that might be a little bit more meaningful to you. I mean, bungee jumping is fun and all, but I did it when I was in my early 20s. I survived. I haven't done it since because it costs a lot of money. But, a bungee jumper, what happens? You jump for a bridge and you go boing, boing, and every boing, the height you rebound gets a little bit smaller, right? That's going to form a geometric sequence of numbers because each boing, the size of each boing, is going to be a certain fraction of the previous size. So in this problem, we're going to 20 to 80 to 32. So we would figure out what's the ratio from number to number. That ratio would be less than 1 because the numbers are getting smaller. And we'd have to go out to the 5th number in line to answer this question. Okay? At some point, you can go back and revisit that. On the worksheet that you'll be directed to, so in Google Classroom is a worksheet with a lot of open problems of this type. You can see a couple of problems about interest on a bank account. So the geometric sequence is the setup for interest rate problems. Say you deposit $2,000. So here's my initial deposit, and it's going to get interest once a year, and let's say it makes 12% interest. So 12% interest per year. It's not compounded continuously or any of that nonsense. It's just once a year, here's your 12%. Okay, well, how do we calculate how much money is there? Well, here's our first number in the sequence. It's 2,000. That's how much money we put in. At the end of the first year or the start of the second year, how much money are we going to have now? Well, we're going to have this $2,000 times an extra 12%. The way you increase this number by 12% is you multiply it by 1 to get back the original 2,000 with the extra 12% in decimal form tacked on. So when you multiply by 1.12, you are increasing that number by 12%. Okay, so that's how much money at the end of the start of the second year. Well, how about a year later? The value that our account is now is that 2,000 times 1.12, but now we're at the end of another year, so we're going to hit it with interest again and multiply it by another 1.12. And this simplifies to 2,000 times 1.12 squared. And remember, that was A3. So like after just a couple of rounds of this, you can see this geometric series formula that we were just working with kicking in. And so we can answer a question like, let's say we're going to let this money ride till retirement. We're going to let it sit for 40 years. How much money is going to be there at the end of 40 years? Well, we could just use the geometric series formula, geometric sequence formula, to just hop right out to 40 years from now and figure that out. Okay, so those are the kinds of things you'll be messing with. So in Google Classroom, the extra page is a worksheet. There's some of just the startup problems about here is a list of numbers, figure out the ratio, calculate the next tuple. There's some problems doing this game where you have a sequence, you discover the ratio, and then leapfrog yourself out to some term far into the future without needing to bother with the intermediate terms. And then there's a couple of problems, sort of like interest problems, that will apply this stuff so you can see why these geometric sequences are pretty important. So have at it.